Hey, 11. Thanks for coming, guys. Really nice to see you all. We've got 11 people online, which is really nice. I'm a bit sad. I'd love to see more people coming, but I do recognize that it's hard with everybody being doing their different things, having dinner and whatnot. I mean, I've got Amira eating cheesecake while watching this. Amira, you need to definitely bring me some cheesecake tomorrow. I'll be very disappointed if you don't. So I'm watching for cheesecake tomorrow. Okay, guys. So today we're going to be doing a crash course through covalent bonding. I'm going to run through as quickly as I can all the bits and pieces that you guys need to know. I'm going to be linking all of it together. So we're going to be doing simple covalent, or otherwise known as covalent, and then we're also going to be jumping into giant covalent as well. So we're going to box it all off this evening. I am aware, though, that the worksheet and the preliminary that I've set you guys is purely for simple covalent. So what I'm actually going to end up doing is I'll probably run a second webinar specifically focused for the giants, even though I'll probably end up having to do that as part of today anyway. And I'll probably send out another set of booklets, a preliminary for giants and a follow-up for giants. I really hope that you guys have had an opportunity to do the follow-up works for the other webinars that we've been doing. Those follow-up booklets are designed to solidify all the bits and pieces that we've been doing, because doing these crash courses, it's so quick and it really is easy to, it's a good revision, but definitely doing some of those follow-up booklets will be really useful. Okay, so I'm going to straight away start sharing my screen. And Amira, you're absolutely right. I owe you some commendations. So I'll pass those over to you tomorrow when I see you guys, when I give you your test results. Okay. So I'm going to share my screen as always. There we go. And I'm going to drop straight away into our webinar. So we're doing a covalent crash course, otherwise known as CCC. This is what I'm going to be covering today. So we're going to be covering several learning objectives. The first one is, when does covalent bonding occur? Be able, so knowledge, of course, the first one. Be able to draw your Lewis dot and cross diagrams. These, of course, are really important for me to look over. I'm going to give you half a dozen GCSE examples for you guys to be able to see the tricky ones that they keep running. And the common ones that keep appearing. We're then going to do the understanding of WIMPs. Now, the word WIMPs, I love WIMPs. I invented WIMPs, but we all in this room know that WIMPs stands for weak intermolecular forces. We're then going to pick up the acidity of covalent compounds, and then we're going to drop into knowing the exam examples, and at that point, that brings to a close the simple. And then I'm going to finish off with understanding giant covalents versus the simples. And at that point, although I will probably run a second webinar just to cover things like diamond and graphite. I mean, graphite needs an entire webinar all on its own, but I will be covering it today as well. But it's going to be taking a bit of a sideline. Okay, so my usual bit then, of course, I'm going to run the crash course first, and then we're going to finish off by looking through our preliminary work that you guys have all been working on. And I've done something rather unusual in this situation, which is I've gone straight to my fifth learning objective. This is the knowing examples, because I'm going to be using all of these examples all the way through the webinar. So we've got group 7. Now, group 7 is quite an interesting one, really, because I think most students don't realize that. Amira, you need to sort out the cheesecake. Oh, don't say sorry, just sort it out. Donna, you ain't getting any. So group 7 does make an appearance in covalent bonding. And this is because, of course, we all know here that the group 7s are all diatomics. Second one is running into crude oil. Now, you guys will remember this, of course, because in the crude oil topic, WIMPs made an appearance. We talked about the idea that the chain length changes in crude oil. We've got a huge selection ranging from C1 to C50, and their boiling points change. And this is all down to the WIMPs that we are forming between the molecules. They're going to drop into ammonia, hydrogen peroxide, sulfur dioxide, diamond, silica, otherwise known as sand. It's nice for me to put the sand. That's sand silica, titanium dioxide, and silicon. And at that point, I'm then going to, of course, end with graphite. Graphite does play an important role, even for the simples, because it involves WIMPs. So, but those guys, again, I'm going to be focusing on these top 5. The reason being, of course, is that all of these top 5s, these are our simple covalent. Now, I do really want to stress this simple word. I'm not a big fan of it. So we're going to be starting off with simple covalent today. And I am very aware that this word simple gets used way too often, including by myself as a teacher. What is silica, sand, the thing that you find at the beach? Yes, that is absolutely correct, Lucas. So silica is just sand. By the way, also known as quartz. Quartz, the stuff that you buy in those big crystals that you find in one Utama, that is, those quartz crystals are just a giant piece of sand. If you run that through the rock cycle, you end up with tiny little grains, and that's your sand that you find at the beach. So, do you know what? I don't like it. I'm just going to kill it, because this is really about covalent. And if someone says the word covalent to me, then you immediately are swung to simple. The giants are special. People often ask me, and this is one of the questions that I immediately want to answer, which is, how do I know when it's giant and when it's a giant covalent or when it's just covalent? I'll say the word simple, but when just covalent. And the answer is because you have to know your giants. Your giants are rare. So the giant covalent are rare. Giant covalents are rare. And what that means is you need to know them. You've got to learn them. And what that means is if they don't fit those 6 giants, then it's going to be simple. And what that often means is when you pick up exam questions, I do an exam question of something like, and I'm going to throw in Wing Kit at this point because he asked such a wonderful question before of boron trifluoride. And this is an interesting covalent compound. And people often, the question with boron trifluoride, type of bonding. I'll rearrange the word type of bonding in boron trifluoride. And the answer, of course, is covalent. It is not giant. It's simple. It's just covalent. I'll put simple. And people go, how am I meant to know this? Because it's not one of our giants, and you know all the giants. So we're going to be focusing predominantly on simples. So, okay. So first thing we want to do is we want to do, when does it occur? When does covalent bonding occur? And at this point, it's an easy answer, and I'm going to throw it out to the classroom. Would anybody for 3 commendations? I'm going to start collecting my commendations immediately. So I'll put commendations. When does covalent occur? Let's see the first person that appears. Answer. Non-metal, non-metal. Thank you, Donna. Donna makes an appearance, gaining her 3 accommodations. That's excellent. So the answer is between 2 non-metals. Between non-metal and non-metal. So I'll put and non-metal. So these guys do covalent bonding. When there is attraction between shared and the nuclei of 2 atoms. Ah, Lucas, what a great answer. But you've actually gone too far, Lucas. Oh, that's a great example of how things can be over-taught. That answer is going to be making an appearance in a minute because I'm going to follow it up with that question immediately, Lucas. And Lucas, your answer is so great, I'm going to give you one, Lucas. I'm going to give you one commendation so far, because that was a great answer, even though it was wrong. When does covalent occur? And the trick here is when, and we're looking at two non-metals. At this point, I have to visit my wonderful, my beautiful periodic table, which I absolutely adore. I love this thing, and it's nice, of course, for me to draw my line. We've got our step ladder. We all remember this. We got this. This is the first time the periodic table gets used in chemistry, and it makes an appearance, of course, to give us our metals and non-metals. So these guys are all of our metals. We've got loads of metals, and we've got our little baby group of non-metals over here. And we realize that when ionic bonding is happening is when you take a metal and a non-metal and you put those guys together. But if you want covalent, you've got to be going for two or more non-metals. And these guys don't exchange electrons, they share them. And at this point, I get to give a whole load of examples. So, go into the classroom. Guys, list as many covalent compounds as you can, and I'll give you all one accommodation for every covalent compound that is named. Impress me, year 11. I'll be collecting them there. There they are. So we've got, I've got a mirror, outstanding. We've got ammonia. We've got water. So Amir is on the board. I love this. We've got a great, so Amir is hit 2 already. Lucas just gained an extra, he's up to 2. I've suddenly realized I need to do this as a tally chart. Yes! Don is on 3, Lucas is on 2, Amir is on 2. Daniel Booth has made an appearance. I like it. Danny B. Danny B, well done. We've got antimony trifluoride. Wing kit. All right, Wing kit, you can have it. It's absolutely right, by the way. So I'm happy to give you it. I'd like the more common ones. We've got bromine from Lucas. He's correct. Lucas giving me ammonium. Lucas, that one is important. Lucas, you're right, but that is not a compound. It's an ion, which means it's going to bind to somebody else ionically. Oh my goodness, I need to make sure I talk about that today. Amir has given me CO2. Wing kits, hit me methane, wing kit, well done. Donna cow farts. Oh my goodness, wow. Lucas, well done. He's hit 4, he's given me iodine. Donna, by the way, farts are methane, Donna. You know this. That's why it smells. I need to make sure that I remember to go over the ammonium ion. Donna, carbon monoxide making an appearance. Well done. Methane had already been mentioned by Wing Kit. Daniel Booth, H2O was already done. Guys, I'll end it there. Well done. You've given me some great examples. Now, at this point, I need to just... Some of those ones you've given me have just been fantastic. CO2, carbon monoxide, sulfur dioxide. Well done. That came from Jin something. Jin, you on there? Jin Yan. Oh, she's on the board with SO2. Great job. Don't know how to. Buckminster fullerenes. Lucas, Buckminsters are making an appearance. They do. Buckminsters are a rather bizarre thing. They do classify as simple, but they often appear in a giant setting. So that one requires a bit of a chat. I'll be talking about that later. So I've got some great examples here, and guys, you need to know these. Let's add some more ones. So ones for the exams. Oh my goodness, do we need? That's a really. Oh my goodness, do we need ammonium? Do we need water? We need SO2. We need carbon dioxide. Other important ones. Other important ones. This is an important one. Hydrogen peroxide. Edexcel, love that guy. All of the alkanes are excellent. Methane, ethane, propane, butane. I was expecting lists being spat out. And what you'll notice is there are no metals to be seen. Oxygen, Donna, well done. Spot on. Oh my goodness, that needs to be there. Oxygen gas, all of group 7, fluorine, chlorine, bromine, iodine, astatine, even though astatine is radioactive and we never talk about her, so let's get rid of her, we don't like her. But these are all covalent. And it's nice that at this point, I really need to make an appearance of ammonium. The ammonium ion that Lucas has now mentioned is a covalent ion, and it looks like this. However, we never see that outside of an ionic compound such as ammonium chloride. And if they asked you for the bonding type of this one, this is year 11. It's only ever been once at GCSE in my 13 years, just once. And that breaks all the rules. That one is ionic. And it's ionic because we have, and it's nice to drop back into ionic bonding, we've got the positive ammonium ion surrounded by the negative chloride ions. That compound is ionic. It's the only example that you need at GCSE that breaks this rule. Do make a note of that. If you're making notes this evening, please do remember that ammonium chloride, it has a much higher melting point than you'd expect it to be. And we'll come back to melting point because we'll do those in a moment. So really lovely to see all of our GCSE examples appearing and for us to see that all of these are non-metals. At this point, we now need to talk about the what is. Lucas, what is I shouldn't capitalize. Poor English. What is a covalent bond? Now, this question is either 2 or 3 marks. And the question itself, nitric acid, Lucas, absolutely right. All of our acids, every single one of them, every one of them. Hi, Mr. Duncan, so I'm late. Sian, it's lovely to have you here, Sian. Thanks for coming. So the covalent bond, this requires you guys to make sure you give really good, concise answers I don't want you to waffle because you guys like to waffle. 3 bullet points. Number 1, it is a shared pair of electrons. I like that. A shared pair. Please note underlining of pair. You can't just say electrons. Hey, Julian, thanks for coming. So we've got a shared pair of electrons. And it's at this point, you guys know, especially those who I teach. I love diagrams. I don't remember that. That is not something I keep in my repertoire. What I have is a diagram. And my diagram is just this. It's that. That is a shared pair of electrons. We have overlapping shells, and I'm filling it in with a dot and a cross. And guys, this is important. I don't know why my laptop keeps sending me back up to here. I haven't got a clue why, but it does. I'm going to try and get rid of some of these windows. Close that down. So that's my picture. Please note, year 11, that this is a dot and a cross. This is not a cross and a cross. This is not a dot and a dot. This is a cross and a dot, and they are next to each other. So this then translates. There's another image. This is diagram 1 in my head. The other picture I have, by the way, I'm going to put some element symbols in here. Let's change my color. Let's put in a hydrogen atom and a chlorine atom. And that picture also translates to diagram number 2, which I have stored, which is this. I'm going to do or. It's a stick. Now, in chemistry, how do you draw? I'm coming to it, Lucas. I'm on my way. So this picture here is super important. Every stick in chemistry, when you see these appear, it's telling you the bonding type. This isn't for fun. This isn't just showing a bond. We are specifically drawing covalent. So now, at this point, I need to pick up another box called bond rules. Bond rules. So this box is worthwhile knowing. And you know what? I often get asked by students, do I have to know them all? And the answer is no. The periodic table is your favorite piece of kit and it tells you them all. But we know hydrogen makes, I'm gonna do this as a table. So this is, let's do this properly. Let's do atom and bond number. I don't even like that word, bond number. This is I don't like it. Let's make this clearer. The number of bonds made. So hydrogen makes one bond. Chlorine makes one bond. Now at this point, I now go, oh, periodic table. Because where is chlorine? Chlorine's over here. And it's nice for us to realize that group 7. I love chemistry. Why do I teach chemistry? Because I don't have to remember it all. I do this because chemistry has patterns. I don't have to. Everyone in group 7 makes one bond. All of them. So bond rules. Bromine has one bond. Iodine has one bond. Fluorine has one bond. They all do. Next one, oxygen. Oxygen makes 2. Carbon makes 4. Nitrogen makes 3. Those right there, folks, will hold you in very good stead for the whole of chemistry. All of it. You pick up additional ones, but those guys will be the most important you will ever learn. So this is where I'm dropping into at this point. I still haven't answered my question. I need to finish this. And I promise I'll come to Lucas's question in a moment. This is a shared pair of electrons, but that's only 1 mark. And where do the other two come from? It is the electrostatic attraction. 1 mark for using that word. It's the electrostatic attraction between the nuclei or the nucleus. Electrostatic between the 2 nuclei, plural, and the shared pair. Now, people often say, I don't get it. So, guys, neither did I. Let's put it in a diagram. Let's put on a nucleus. Let's put on a nucleus. Here's our nucleus center. So there's our nucleus, which contains all the protons. And the protons are positive. I'm going to have one over here as well. Nucleus with more protons and neutrons, but they don't matter. And then my electrons are going to be sitting in the gap. And I'm going to have, and do you know what? Let's change the diagram. They look like this, and they're negative. I now have an electrostatic attraction that holds those guys together. Nucleus. Nice, Lucas. That's quite funny, really, actually. I like that. Okay, so there's our 3 marks. And year 11, please be warned. If you're not sure what they're asking, give all 3 bullet points. That just guarantees you all the marks. Okay, so we've done what is. We've also done our examples of them in non-metal. We now need to do multiples. And at this point, I drop into my dot and cross Lewis diagram. And it's nice for me you've got to know that word Lewis, because sometimes they completely ignore the word dot and cross. They just say, draw a Lewis diagram. So at this point, it's nice for me to mention more than double and triple bonds. So EdXL, this is where I drop into the exam examples, because they love some of these more than others. And the one I need to talk about is carbon dioxide. This one, even my A-level students, I have not heard okie dokie in ages. Yeah, absolutely, Amira. Yeah, I'm taking medication for it. It's fun. So, carbon dioxide. Now, my A-level students, when you take a little bit of a step up in this, it always becomes a bit tougher. And what they do is they start pushing you outside your comfort zone and they start asking you for people you don't know. That requires you to be building something rather than just doing it straight out from memory. So the first thing to realize is there are 3 atoms here. Let's convert this into a stick picture. I have carbon joined to 2 oxygen atoms. Now, carbon must make 4 bonds, and oxygen must make 2. So this makes sense. We've got the carbon making 4 bonds, bond number 1, bond number 2, bond number 3, and bond number 4. Carbon is a happy chappy. Oxygen has got, if I now do oxygen, this one's in pink, here's my oxygen, here's his 1, and here's his 2. She's a happy chappy, a happy girly as well. Same from this guy, this girl. Yeah. So, now, students, when I teach chemistry, what you realize is I'm not just teaching you chemistry, I'm teaching you methodologies, ways of making this easier, making it stronger, making your ability to answer questions, your understanding better through methodology. And people often try to skip the sticks, and you should never skip the sticks. You should always drop in a stick diagram before you start a Lewis, because it's going to really, really help. So I've got 3 atoms, which means I've got 3 circles and 2 overlaps. So I draw my 3 atoms and I overlap them to join them together. I put on who they belong to. Students often ask, how do I know who goes in the middle? Probably the one that you have the fewest of. I'll show you another example of that in a minute. And at this point, I go, oh, each of these sticks represents a shared pair of electrons. And each of those pairs is a dot and a cross. So at that point, we can start filling in the gaps. I've got a dot and cross and a dot and cross. It is not, and I emphasize this, it is not that. That does not happen here. This is a GCSE. All of them are dot and cross, dot and cross. Now, at this point, I need to consider. And here is the first most, this is the most important so far in this webinar point I can make. You've got to make sure everybody is happy. Carbon is happy. Why? To the classroom, please. Why is carbon happy? First person, I'll give a commendation for the first person to give me that, please. Find my commendation list. Nope. Who's going to get it? There they are. Donna. No, Donna is incorrect. All valence electrons in bonds. Lucas, that is actually the wrong answer. You've overthought it. I love that, Tiffany. No, you're wrong, Tiffany. No, I still haven't had the right answer. You've gone to my bond rules. You've not thought about the main point in bonding. Why are they doing it? What are they all trying to achieve? Come on, folks. Who's going to get it? Full outer shell. Donna, I'm going to give you half. No, and we need numbers. Why is it full? Full octet. Oh, I love that, Winkit, using the word octet. It's such a forgotten word, octet. I love that. Neutral, Daniel, no. 8, Donna, Winkit, you can have it. There you go. Donna and Winkit gain 1. So I love people quoting the bond rules. But the problem is the bond rules are they're not enough. It's all about having 8. So we're realizing it's happy because it has 8 electrons. It is sharing. It's got 4 pairs, but it is currently holding on to 8. So it's done. The problem is oxygen is not done yet. Each oxygen here, let's look at a particular one. This oxygen has got 1, 2, 3, 4 electrons. It is not happy. So how does it become full? Well, of course, oxygen started out with 6 in the first place. So it's got 4 circles here, 2 circles, 2 circles, and then it's other 2 which were hers originally. Oxygen had 6 originally, which means it's now got to 8 having made those 2 bonds. So the other one, of course, also needs balancing. So there's carbon dioxide. It's a tricky one. Right, year 11. Now, the problem is, of course, if you're in class, we'd be doing a whiteboard activity. Let's go. Let's really push out the boat. Let's look at some of the really tough examples. And I'm pulling these, by the way, straight out of A-level. Let's look at nitrogen gas. This is a clever one. Because number one, first thing I do is sticks. I've got N and an N. How many bonds does nitrogen make according to my rules? It makes 3. And each of them needs 3. So there are the 3. They're both happy. They're both done. So now I need to turn this into a Lewis diagram. Circle and circle, one for each of my atoms. Put my symbol in. Right, how many, year 11, are going to go in the gap? How many electrons are in that gap, folks? Next one, let's go back to my commendations. I need to put my commendations somewhere else. I'm going to be traipsing through my presentation the entire time. Lucas, well done, Lucas. Gaining an extra one there. I like it. I love that. 6, 6, 6, 6, 6, 6, 6. Yeah. So we're going to have 6 in the gap. Let's put them in. And they're going to go in as they always do. Dot, cross dot, cross dot, cross dot. So they've got 6. There are the 6 electrons in the gap. 3 pairs, 3 covalent bonds. But neither of them are happy yet. Now, the reason, of course, why is because they're not at 8. So how many did they have originally? They were in group 5. Now, going back to the periodic table, group 5. Why do we break up the periodic table into groups and periods? Why do we do this? Because the periods tell us the number of shells. This is 1 shell, 2 shell, 3 shell. And then the number in the group tells us the number of electrons in the outer shell. So let's now clean this up and find out how many nitrogen has. Nitrogen is in group 5. Each of them had 5 electrons. Well, 3 of them came from each one. So each one, that one will need 2 extras. Now there are the 5. And what you notice is 6 plus 2 equals 8. And the other one is crosses. So, and now both of them now become happy. So everyone's now full. Everyone's got their 8. It's a great example. Nitrogen gas, and students really struggle with it. So, okay, let's go to another really interesting example. Let's go for ethene. Notice this is not ethane. This is ethene. What that means is we have a covalent double bond between the carbons. Let's turn it into a stick. Now, year 11s, you've probably only just been working on, some of the year 11s will be further on than others, but we're talking about organics recently, and we've been doing alkanes, and some of you won't have come across alkenes yet, but alkenes are about a double bond. So we've got 2 carbons, we've got a double bond in the center, and each carbon then has 2 hydrogens. So this is ethene. It's a great one. Now notice, everybody's happy in terms of bonds. Hydrogen makes 1, and carbon has got 4. Let's turn this into the sticks. Circle carbon, circle hydrogen, hydrogen, and hydrogen. Right, let's now fill in the letters. Carbon, carbon, hydrogen, hydrogen, hydrogen. Right, now just fill in the gaps. Well, the hydrogen's always single bonds. So let's just lob in a dot and cross into each of them. And then the carbons have got a double, which means they've got a dot and cross and a dot and cross. And it's all over. So this process of stick to Lewis is quite important. It will help. I promise you it will help. Now, other examples, which GCSE, going back now from A-level into GCSE. By the way, ethene has made an appearance several times. But now I need to go to somebody like hydrogen chloride, HCl. Why? Because we see this diagram. See that diagram? Carbon makes 1, chlorine's in group 7, they all make 1. It's turned into a Lewis, 2 circles, 2 atoms. Put in a H, put in a Cl. There is 1 bond. Juan bond. So we've got 1 pair, and it's a dot and a cross. Now here's what's special about this, because hydrogen only has 1 shell. And the first shell, will you die if you inhale hydrogen chloride gas? Lucas, definitely. it'll turn into hydrochloric acid in the fluid in your lungs, dissolve your lungs from the outside. You'll spit up blood. I've done it. I actually breathed in chlorine gas, which reacts with the water turning into HCl. And I coughed and I ended up in the hospital briefly. I breathed in a huge amount of chlorine by accident, and I coughed up a whole load of blood, and I got rushed into A&E. It was fine. A couple of hours, I was there, I stopped coughing. So this one's important. Hydrogen has only one shell, and that first shell only holds two, which means hydrogen's happy. This is important. Hydrogen's thinking, woo, full baby, don't need 8, only need 2. But chlorine, on the other hand, everyone leaves it like that, and it's not over. We put chlorine's other 6 on. So it's nice for me to, I'm just going to highlight that one. There was chlorine's 7 electrons that it had originally. What's the chemical that eats you from the inside? Amira, the answer is probably hydrogen fluoride. Hydrogen fluoride is another acid, but it's a rather odd acid because it's so small it passes through your skin and dissolves your bones. It's not a nice one. HF, nasty stuff. So now everyone's happy, but it's these additional electron pairs that everybody forgets. People forget. Please make sure everyone's got 8 except hydrogen, which only needs 2. Okay. So, okay. We've come across Lewis and we've worked through it. Now, really, I'm going to scroll all the way back and have a look through some of my other examples if I can. Hydrogen peroxide. Okay. I'm trying to figure out. Right, so we've done when covalent, we've done drawing, dot and cross. We're going to be coming to WIMPs shortly. I'm going to give you a couple of others. I'm going to do some. I'm going to do hydrogen peroxide and SO2. So hydrogen peroxide, H2O2. Right. We've got 4 atoms. Let's draw a picture. Hydrogen only ever makes 1 bond. Oxygen needs to make 2, and it joins to itself. So we get H2O2. It's a rather odd-looking molecule. Not particularly stable, decomposes in light. That's why we store it in a dark bottle to protect it from UV. So this molecule has got 4 atoms. Let's turn it into the circles. 4 in a row. Let's add in our symbols. We've got H, we've got O, we've got O, we've got H. Now add in your pairs. 1 bond for each. Dot and cross for each. Now hydrogens are happy because they've all got 2. They're like, yeah. Oxygen, however, not done. Oxygen's only got 4 each. So that takes it up to 6. That takes it up to 8. The 6 circles were oxygens originally. 6 circles, and we're happy. So there's hydrogen peroxide. This has come up several times at EdXL. They do like this. Partly because, of course, you come across it in catalysts. If you take hydrogen peroxide and you pass it over a catalyst, and you don't need to know the name of this one, potassium permanganate, manganese dioxide will do it, and you'll get water and oxygen gas. This comes up quite a lot. I like to balance them as well, 2 and a 2. So this appears quite a lot. It's part of the elephant toothpaste demo to make oxygen gas. It's quite a rare gas to make as well, but they do like asking about it. So there's hydrogen peroxide. Let's now do SO2, sulfur dioxide. Guys, this is now much harder because look, sticks. How many bonds does sulfur make? Now, annoyingly, you're not going to like this year 11. This is why this is now part of A-level. Because sulfur is in the same group as oxygen. Should make 2. And it does sometimes. But in sulfur dioxide's case, it makes a double bond. So, and awkwardly, we've got 3 atoms all linked together. Oxygen must make a double. So each gap is dot cross, dot cross, dot cross, dot cross. Oxygens need to get to 8. And here's the bit you're not going to like, year 11. Now, this is part of A-level, which is sulfur had 6 originally. Let's call the 6 X's. Let's call the X's sulfurs. Well, she's not got enough. We need to add another pair. That's actually what sulfur dioxide looks like. And what that means is, yes, it's broken the octet rule. Now, the reason why I mention this is because it has appeared once at GCSE, just once. And they gave you that diagram. And the question said, why would a student question the above structure? And what you'll notice is in the question, they are not trying to get you to explain it. What they're wanting to see is that you can say why it doesn't fit what you've been taught. The answer, 2 marks. The answer, can anybody help me out? 2 bullet points. What do we need? Why is this picture? Why would students not like that diagram? 2 commendations up for grabs. I know there's a delay. Is it because we don't know how many bonds sulfur makes? No, it's not. Lucas, 6 valence electrons, nothing to do with it. Siam, none of them have full outer shells. No, they do. Oxygen's full. Lucas, however, makes 4 bonds. No. Donna, winner! Well done, Donna. Well done. Donna gains it. Guys, you have learnt key facts. Donna, 2 bonuses. You're doing so well, Donna. You're up to 7. So there are 7 valence electrons. That's correct. Well done, Sarah. You're too late. Winner, winner, chicken dinner. Mel's, Donna's smashing through this now. So why is this weird? And she's absolutely right. I'm just giving my laptop a hide. Giving my laptop a little bit of time. It's not liking this very much. It's really, I need to speed it up if I can. Oh, it's because I've written so much on it. It's not liking this very much. Oh, come on. Let's click on something else and go back to it. Oh no, sorry folks, hang on a minute, yeah, I know. Oh, mine is like, there we go. Right. Sulfur dioxide. Why would a student question the above structure? First bullet point, sulfur. Sulfur has 10 electrons in its outer shell. It has 10 electrons in its outer shell. Guys, that's not normal. Not at GCSE, it isn't. We know first shell holds 2, second shell holds 8, third shell holds 8. I ain't saying that. But it definitely doesn't hold 10. So sulfur has too many electrons. So what's the second mark? Sulfur has 10 electrons in its outer shell. 8 electrons. 8 electrons usually needed to be stable. Or you could have even said full. So what a lovely question. And you can see what they're doing. What a lovely way of being able to ask you, how many electrons do I need before I'm stable? What is considered to be a full outer shell of electrons? Why are noble gases full? 8, 8, 8, 8, 8. And then you get to this one and they say, why is this not normal? Because there's 10. And you're expecting 8. It's just such a lovely, lovely question. So it's only ever come up once, and it's nice to go that little bit of an extra mile to see that things are not done yet. Everything's going to continue to add another layer as we go on. So lovely to have sulfur dioxide make an appearance. Ammonia, hydrogen peroxide is done. Okie dokie. So I said it again. I'll go and take some of my medication in a minute. So, okay, at this point, we drop into our next section, which is on WIMPs. So this is what we're now focusing on, WIMPs. So I'm going to teach this in my usual. I can imagine the students panicking when they saw that question. Oh, yeah, they really, really did. They were like, hang on a minute, yes. And do you know what? I like to say to you guys, especially those I teach, you know, I try to teach as much as I can. I'm never going to cover everything, but I hope, what I pray and what I try to do is to give you guys the confidence in what I'm giving you. You know, I will give you everything I can and enough. Everything that I will give, it will be enough for you to answer every question, but I can't predict those crazy ones. But hopefully you'll have enough confidence in what I've taught you to be able to go, hang on a minute, I can apply this to a setting I don't recognize. So having confidence in the chemistry that's been delivered is important. Again, so WIMPs. So I invented the word WIMP because I realized when I was teaching in my very first school that students really struggled with 4 words: weak, intermolecular forces. That what I think was happening is they were getting through halfway through this and going, oh, I'm bored. But what was our last word again? And it's exactly what they were doing. So I wanted to make it easier. I wanted to make it simpler. I wanted it to make it funny. I wanted to make it memorable. And WIMPs just works really well. And you're going to be using these a lot. And these come into one particular question. So the question is explain. And we'll see these in our questions in a bit. Explain why, and they're then going to drop you into an example. They never give this outside of an example. You might say, explain why water, explain why carbon dioxide, explain why methane has a low boiling point, BPT. So at that point, now, can I just say, this is bonding. Oh, Amira is already on it. I love it. Her S has already appeared. Now, this is Susan Boyle sings Nelly the Elephant. We've got off. This is a 5-mark question. And please forgive me, year 11. They're not going to offer you that. It's going to be 2. And you'll see this in a minute. But I'm going to run all 5. This is my bread and butter in chemistry. So the first one, structure. So what is the structure? Let's pick on someone. Let's do water. What is the structure of water? 2 non-metals. This is simple. Don't like it. You don't even need to say it. It's just covalent. This is covalent. Simple. Covalent. Bonds. Now this one. Now I'm going to show you GCSE and then step into A level. For GCSE, there are weak. I'm just gonna say WIMPs. There are weak intermolecular forces between the molecules. GCSE. Between the molecules. You will not, first of all, folks, you are not allowed to use the word WIMP in your exam. You must use the word in its entirety. So there are weak intermolecular forces between the molecules. Strength. Well, they're called weak for a reason. They're very weak. Number. There are very few. Therefore, the energy to break. Very little energy needed to break. You're done. The A-level bit, you've got to go a little bit of an extra. You've got to say bonds. There are covalent bonds within the molecule and weak intermolecular forces between the molecules. We even then have to select the type of weak intermolecular forces there is. I don't want to go into that. But weak intermolecular forces between the molecules, they're very weak, very few, very little energy. We're done. So now here's what I'm now going to do is I'm going to highlight where are my key bits, right? Covalent. I'm going to try that again. Covalent structure. Weak intermolecular forces between the molecules. Very little energy needed to break. I don't like this. I hate it when Edexcel make me choose. So guess what I do here, 11? I don't. I just give it all. Why would you ever do anything else? This is routine. This is methodology. I want to teach you a method to gain every mark with absolute clarity, with absolute assurity. There is no, you get to walk away going, smashed it, every point's there. I'm not going to lose a single thing. You know, I don't like this, how they pick and choose. Don't. Just give it all. If it's in a tight space, just comma them. Covalent bonds, structure. The structure is covalent. Bonds between the molecules are weak intermoleculars, which are very weak. There's very few of them, and therefore very little energy. Just do it in a big long sentence. You'll get it all. So, now that, just to say, the bullet points are great, aren't they? But I don't like words. I like pictures. Pictures are what I keep in my head. Here's water. And here's a molecule. And here's another water, which is a molecule. And between them, there are weak intermolecular forces. So within the molecules, we've got covalence, but between them, we've got WIMPs. So if I take H2O liquid and I add heat, what do I make? I make H2O gas. I do not break the covalence. I make just, let's change the picture. Here are my WIMPs. There's, and here's gaseous water. All the WIMPs are broken. The H2O is still H2O. You've just broken the WIMPs. That is the picture I have. Will I lose a mark if I say steam instead of H2O gas? They actually, Lucas, they love to ask about steam. So H2O gas has two names. It is, number one, water vapor. And the other is steam. Two names. And they often have to give the common name for H2O gas. Why can't you just say water vapor? You can. It's just, I'm just telling you that there's another name for it, and they like to ask it. Absolutely, steam is the other one. Well done, Quayshan. Right. So it's nice to cover our WIMPs. Now what I want to do is I want to put it into a more of exam setting, because group 7 and crude oil now need to make an appearance. So this is now WIMPs in exams. Now we come across it in 3 questions. Question 1, explain low boiling point. Explain low BPT. Done that. Tick. Susan Boyle sings Nelly the Elephant. Simple covalent. Weak intermolecular forces between the molecules. Strength is really weak. Very few of them. Not much energy. Question number 2. Explain the trend in group 7 boiling point. So what happens in group 7? So we've got fluorine. Terrifying fluorine. Fluorine has a boiling point. This is where, let's go to Google. I don't know what it's doing. That one. So I hate guessing. It's in the minuses by a mile. Fluorine BPT. I don't know if it's going to let me do BPT. It's so not going to. I hate that. I really wish it would. Fluorine boiling point. So, and it is minus 188. Chlorine. I'm going to say about minus 50. Oh, I love it when I get, because I have to check it and see if I'm close. Chlorine, come on, minus 50, minus 50, minus 50. Minus 35, damn it, so close. Minus 35 for chlorine. Bromine, right, guys, these two are gases. This is the first, and one of two liquids on the periodic table. Brown liquid, absolutely terrifying. I'm going to say a boiling point of plus 80. I'm going to say it's about 80 degrees. I'm going to be way off. Oh, no. Come on, give me 80. Come on, be closer. Bromine, come on, 80. Come on, 80. Come on, 60. 60 plus 58 degrees Celsius. Next, right, iodine. Iodine is now a solid at room temperature. I'm going to say it's got a melting point of about 150. Oh, no. This is the problem. I don't know my melting points. It's madness, really. 150 for iodine. It's so going to be more. 184. I wasn't far off. I'm happy with that. 184 degrees Celsius. So the trend is, in their graph, it is climbing. So they're getting bigger. So we can now predict astatine. We've never done it. Never been done, folks. Astatine, it holds a Guinness Book of World Records. It is the rarest element on the entire planet, 2 grams. So what would its melting point be? Look at the trend. That's gone up by plus 150. Then it's gone up by plus 90. Then it's gone up by plus 130, something like that. Something like 60 to something like that. So what's this one going to do? It's going to be somewhere in the middle. Let's do plus 100. I'm going to say 280 degrees Celsius. Let's Google it. I love chemistry and its patterns. It makes me so happy. I'm such a nerd. I know. Astatine. 336. I wasn't that far off. 336. Not bad at all. I would have got given that in an exam. So there's a trend. They're increasing in boiling point. So the question is, why? The answer is, they're getting bigger. Well done, Lucas. Fluorine. Oh, get to do our dot and crosses. Here's baby fluorine. Oh, such a cutie. Here's fluorine. Terrifying lady, but very small. There you go. So there's fluorine. Let's have a look at chlorine. Got bigger. She's got an extra shell. Note, she still has only one bond. All of group 7 make one bond. Let's look at bromine. Oh, bromine's much bigger. Now, one shed pair. It's got 4 shells. Getting big. What does iodine look like? Oh, she's enormous. That is a big. She's got dozens. She's got like loads of them. So there's iodine. They're getting bigger. Now, why does this make any difference? You know what? Iodine just isn't big enough. Gonna make her bigger. Yeah. Yeah, here she goes. Amazing. So here's iodine. Yeah. So they're getting bigger. Now, what this means is, as they're getting larger, bigger molecules have stronger WIMPs. Note stronger. Not more, but stronger. They have stronger weak intermolecular forces. Now, it links into group 7, but it also links in, of course, to crude oil. So this makes the appearance in crude oil. In crude oil, we know that we have the homologous series. Gotta love that. Homologous series of alkanes. And what happens is they get longer. So we start off with propane, butane, pentane, hexane, heptane, octane, nonane, decane, and the chains are getting longer. There's 1 carbon, then it gets bigger to be 2 carbons, and then 3 carbons, and before you know it, You've got them in the 20s and the 30s, and the molecules are getting bigger. So we come across fractional distillation of crude oil, and we run our 6 points. Vaporize. Tower has a temp gradient. Tower is hot bottom, warm top. Warm top, followed by gas. Gas rises up until boiling point and condenses. Bigger molecules, and that's it. Bigger molecules have higher boiling points. They don't ask you to explain it here, because you just say, therefore, longer appear at bottom, appear lower in tower. That question killed me in the mocks. I know it killed everybody, don't worry about it. But there it is, the molecule points. And now we can tack on a real reason. Due to stronger WIMPs. Isn't that nice? Covalent bonding explains the fractional distillation bullet points. Everything in chemistry ties together eventually. So, WIMPs are cool. It's nice at this point. I'm going to go over to my... Whoa. Let's go back to that. Over to my learning objectives and tick off a few. We've done group 7. We've done crude oil. We haven't really talked about so much about ammonia. We did the dot and cross. I don't think we actually even did the dot and cross for that. Dot and cross for ammonia. NH3. I've skipped a step. NH3. Don't ever skip it. Nitrogen makes 3. Hydrogen makes 1. Dot, cross, dot, cross, dot, cross. The hydrogens are all happy, but nitrogen is not. We've got to add the lone pair on top. They do that a lot. So there's ammonia. Skip over to here. Right, so we've done hydrogen peroxide, we've done SO2. Right, I think at this point it's 8:05. I'm not going to go to the giants. I'm going to leave the giants for another time. Got graphite there. Covalent within the layers. And WIMPs between them. So the layers can slide. Isn't that nice? Anyway, we'll come to that on a separate webinar. Right, let's have a quick look at learning objectives. Okay, acidity. It's a good idea. Acidity. I just need to mention this. So we know that this comes up quite a bit, actually, and it's important. So I put it onto my learning objectives. So we learned that if you have some oxide and they ask you for its pH, and the answer is going to be why? Because the ions are basic. They're based with water, sodium oxide to hydroxide, and hence why it's an alkali. But then on the flip side, we get to our covalents. Sulfur then after school revision tomorrow. Absolutely, of course, there is Lucas. I'll be absolutely. Oh, blind kicked off my webinar. And I don't. It's just kicked me. I don't know why. Oh, I'm back. I think he's lagging. I think I am lagging, which is really frustrating. I really feel like I need to try and get closer to my Wi-Fi. I've got as close to my Wi-Fi as I can. Oh, could you please repeat what you said, Connor Casey? It's you. I know I'm cutting off. I don't really know what to do about that. Oh God. I'm back. I'm back. Right. I think I'm back. No, it's cut me off again. Oh, no, I'm back. This is being really irritating. Okay, back to this. So, sulfur dioxide, I think, can hear you, you know. That's really funny. Yeah, I've cut across. I've gone to my normal one now. Okay, so the covalent compounds are the exact opposite. Rather than being ionic, rather than being acidic, I've lost my flow now. Oh, it's cut me off again. It really is struggling with this. Don't know why. Clear. I feel like I want to try stopping my MacBook. I'm going to have to get rid of my chat. Well, we'll leave it like this and see if I can bring it back. So covalent compounds are the exact opposite. Rather than being basic, they're acidic. And the question is why. By the way, you never get asked for the equations. Yeah, probably. So sulfur dioxide reacts with water to form H2SO3. Now, year 11, stress this. That is not sulfuric acid. This here is sulfurous acid. So it's not sulfuric. Sulfuric is H2SO4. Please note that. Yeah, sulfurous is H2SO3. This is what happens when we leave SO2 in the atmosphere. Reacts with water to turn into H2SO3, which is a weak acid. This is acid rain. If it was raining sulfuric acid, it would burn everyone's face off, but it doesn't. It makes sulfurous acid. So I can also show you another one, which is the carbon dioxide. Carbon dioxide does the same thing. Reacts with water to form carbonic acid. That's carbonic acid. Let's look at another one. Hydrochloric acid reacts, hydrogen chloride, reacts with water to form hydrochloric acid. So all of these covalents are acidic. And this bullet point is just a nice, easy one to assimilate. Covalent compounds have low pHs compared to the ionics, which have a high. I just wanted to cover that. Okay, this is why acid rain is caused by sulfur dioxide. Right, no examples, we've done it, and I'm going to leave the last learning objective. Right, guys, it's been an hour and 10. Let's skip through our test. So, first things first, write an equation for the reaction. Calcium carbonate, guys, limestone makes a regular appearance. It's one to know. Calcium carbonate plus nitric acid. You've got to learn your acids, folks. You can't make these up. Learn your three. Hydrochloric acid, nitric acid, and sulfuric. Learn those formulae. You can't make them up. We're going to form calcium nitrate and carbon dioxide and water. You remember, whenever you have a comic, salt, water, and CO2. Next, one of the trickiest questions on the preliminary booklet, this one. State 2 reasons why the student's setup is not suitable for collecting carbon dioxide. Now, what I immediately did was I highlighted the 3 problems. So I went, number 1, the gas jar is already full of air. We always collect underwater because we need water to be able to be displaced so that we can collect the gas. If it's already full of a gas, you're not going to displace it. So that was number 3. The first one I spotted was that the delivery tube is only just in it. Most of the gas, by the way, carbon dioxide is heavy. The carbon dioxide is going to trickle out and just fall down. The reason why it's heavy is because carbon dioxide has an MR of 44. Carbon being 12, oxygen being 16, and there's 2 of them. 12 plus 16 times 2 equals 44. Well, the atmosphere we're breathing is a mixture of nitrogen gas and oxygen gas, 99%. Well, nitrogen, which is element 14 times 2 is 20. And there's 79% oxygen, which is oxygen 16 times 2, which is 32. 1% of that. Well, if I times that, it'll give me an average MR of which is heck. So it's just going to pour straight out the tube. We should collect it underwater. The second thing is this is going to make gas, and the gas is going to go straight up that thistle funnel. Yeah, and it's going to escape through there. So 3 options you could have gone for. I went for delivery tube not completely in the jar, so the gas will escape, especially CO2 as it's heavy. Next one, produced in reaction. Oh, gas produced in reaction will go up into thistle funnel instead of gas jar. Gas jar already got air in it. Next. Right, the next one. Calcium sulfate. Right, they asked you to explain. This is quite, by the way, this was a lovely question. The student then set up the apparatus correctly, but he used excess dilute sulfuric acid instead. The reaction produced calcium sulfate. Explain why the reaction stopped, even though there are still unreacted chips and unreacted acid. So the reason why is the calcium sulfate they're forming is insoluble, which means it's going to coat it. It'll form on the surface of the chip, sealing it from the acid. And then I drew a little diagram just to show it. I thought that was quite nice. The sulfuric acid will react for the first few minutes and then stop because it'll form this insoluble layer which will seal it off, a bit like aluminium oxide does. Next, carbon dioxide is bubbled through water, universal indicator, pH 6. What does this say? It is weakly acidic. It's nice for me to do the year 11 bit, which is carbon dioxide's reaction with water to form carbonic acid, and then it is in equilibrium. It is only partially ionized in water. Next, explain what is meant by covalent bond, 2 marks. We've done this already in the lesson. Shared pair of electrons, the electrostatic attraction between the shared electrons and the 2 nuclei. Explain why carbon dioxide has a low boiling point. Why? Bullet points. There are weak intermolecular forces between the molecules and they don't need much energy to break. I would have happily run Susan Boyle in its entirety on that one. Next one, carbon dioxide making appearance for its dot and cross. Next, we're cruising through this. Right, I love this one. Which one is noble? E, it's full. Which one contains 3 protons? It's B, it's got 3 electrons. Which one's phosphorus, which is F? Elements in group 4 are C. Elements in period 3, which is F, because it's got 3 shells. Full shell is E, noble gas. Complete the sentence. Covalent bond, electrostatic between the shared pair of electrons and the nucleus of the 2 atoms. I love this one, my favorite one on the page, on the whole test. D has got 6 electrons, but A has 1. A is going to lose it. And I'm going to need 2 A's to fill D. The formula would have been A2D. The A goes first because it's acting as a metal, because it's losing. Next, give the arrangement, show the dot and cross diagram for hydrogen. It's only got 1 shell. People put 8 in, please don't. Explain why it has a very low boiling point. There are weak intermolecular forces between the molecules. These require very little energy to break. I gave the full Susan Boyle for that one. Simple covalent twins between the molecules, very weak, very few, very little energy. Say what is meant about the term isotope. Atoms with the same number of protons and electrons, but a different number of neutrons. And then I gave the maths, because hydrogen 1 has no neutrons at all. Hydrogen 2 has 1 neutron. Remember, because the isotopes, this is the mass number, and the mass number is telling you what's in the nucleus. So the bottom number is protons, the top one is protons and neutrons. So this has got 1 proton, thanks to this guy, but then it has 1 neutron, because of that guy, and then 1 electron, because it always balances. Next, complete the table. I thought that was relatively easy. Heat transfer, exothermic. Write the chemical equation for hydrogen. How many people forgot their pairs? Don't forget your pairs. Give the chemical test for water, year 11, learn your tests. Anhydrous copper sulfate turns from white to blue. Describe the physical test for purity. Guys, this comes up a lot more than I thought it was going to. You test water for its boiling point and it will boil at 100. Next. Oh, I really like this one. Suggest why a teacher would use a fume cupboard to prevent toxic gases escaping and harming people. And bromine, chlorine, and iodine all release toxic gases. Use the information to explain the order. 1 mark for that guy, giving the order. Most reactive, least reactive. 1 mark, followed by chlorine is very bright, iodine is bright, and iodine was dim. I have literally just lifted it straight out the table. It says use the data. So you've got to use it. Next. Okay. Really lovely question. Wasn't my favorite, but it was close. A student states that the order of reactivity can't be found from this experiment because bromine is a liquid, chlorine is a gas, and iodine is a solid. Evaluate the student's statement. It is very, so what's the problem? It would be very difficult to have the same quantities of each. Because chlorine especially is a gas, you've got hardly any of it. Bromine, you've got loads of it as liquid, even more as a solid in iodine. So the quantities would be very hard to maintain. Gases, we know, everyone here knows, that gases react more quickly than liquids. So immediately there's a variable here you can't control. There are fewer collisions in solids. So I'm just explaining and evaluating by giving bullet points that are clearly useful in why I couldn't do this. Bear that in mind. Another one, testing if your pairs. When you take hydrogen chloride and you dissolve in water, it forms hydrochloric acid. Don't forget to balance your equations. The particle in ammonia is a molecule. It's definitely not an atom. It's definitely not an ion. And it's definitely not a lattice unless it's ionic, and that's covalent. That's ammonia is covalent. Ammonium chloride is ionic, but ammonia is covalent. Which type of bonding is present? Covalent. And what is the formula? NH3. Guys, that brings us to the end of my webinar. I really hope, I'm going to do one on giants. I'm going to do one completely, I'm going to do stop sharing. Bring me back. Year 11. It's been really, really nice. Mr. Duncan, isn't it vaporized before fed into the tube? So it isn't state irrelevant in the question. Does it say that on the paper? No, it doesn't. Oh, does it? Halogen vapor. Oh, yeah. Huh. You're absolutely right. So evaluate his statement. Order cannot be found because it's a solid at room temperature. Right, so you're going to have to heat it more. You'd have to have iodine. For iodine to be a vapor, you're going to have it at a higher temperature. So then if the temperature is different, I've just got that question wrong. Lucas, well done. I just totally got that wrong. That's amazing. So anyway, it's to do with temperature. Because in order to have iodine as a vapor, you're going to have it at a much higher temperature. What that means is you can't compare the two because you'd have to compare them all at the same temperature. Because we know that temperature increases the rate of reaction. I'm devastated. I made a mistake. Lucas, outstanding. I'm going to give you a bonus extra commendation. Year 11, this has been an absolute scream. Thank you so much for attending. I'm so sorry that my computer had a bit of a hissy fit in a minute. For a minute in the webinar. Thanks so much for coming. I really hope it was useful. I will see you all next week on Tuesday. I can't remember which is the webinar we're doing. I'll send you all out the reminder link as always. Thank you so much for attending. I hope it was all really useful. Thank you for everyone coming. Thanks, Jan. Thanks, Dana. Thanks, Little Alda. Thanks, Tiffany. Thanks, Yehun. Thanks, Amira. Thanks, Lucas. Guys, shout out to all of you. Thank you so much. It's been great to hang out. Have a nice rest of your evening, folks. Ciao.